It's almost mind-blowing how massive language models get the order of words.
Right.
That basic idea of sequence is just so critical to how they make sense of language.
Absolutely. Without some way to tell the model where each bit of info is, it's like putting together IKEA furniture with no diagrams. Positional encoding gives it that map.
And one really effective, widely used way, especially lately, is rotary position embedding, or ROPE. It's super efficient, doesn't add tons of parameters, and it handles really long sequences impressively well.
Yeah, and what's really cool is seeing rope E, which, started with 1D stuff like text, now getting used for more complex data like 2D images in computer vision or even in multimodal models.
Which brings us right here today. You, our listener, actually sent us a really interesting paper that digs deep into the math behind ROPE, how it works fundamentally, and maybe how we can push it further for this tricky, complex data.
Exactly.
And since you shared it, you probably already know about transformers, or at least the basic idea that AI needs to get sequences, so we can kind of jump into the weeds a bit.
Perfect. So our mission today is to unpack the mathematical guts of ROPE, especially how this paper rethinks and generalizes it. We want to get to the core stuff that makes it tick and look at these new directions.
Because, yeah, when you think about going beyond just a line of text, say, to a 2D picture, it gets way more complicated. How do you encode a pixel spot using both its row and its column? And maybe more importantly, how do you capture the connection between the row and column? Just doing each one separately feels, I don't know, like it's missing something.
That's exactly the problem this paper tackles head on. Applying 1D ROPE to each dimension on its own is fast, sure, but it just misses those interactions between dimensions.
Right, like trying to see a diagonal line in an image.
Yeah.
If you only look at rows then columns, you might not really see the diagonalness.
Precisely. That combined structure gets lost.
Okay, so let's get into this paper's approach. Right away, it talks about two key properties, relativity and reversibility. What's the deal with those in ROPE terms?
Okay, so these are like the two commandments for good positional encoding. Relativity means ROPE can figure out relative positions from absolute ones. Think queries and keys in attention. And the neat part is, by encoding the difference in position, the model generalizes better to longer sequences or shifted ones.
So it's not just knowing where a word is, but how far and which way it is from another word.
Exactly that. And the paper gives this equation, Rx1QT, Rx2K equal QT Rx2 by 1K. Basically, it shows that applying ROPE Rx to a query Q at position by 1 and a key K at by 2, well, the interaction between them ends up depending only on the relative position by 2 minus by 1.
Ah, I see. That relative part is key for generalizing.
Super powerful.
Okay, makes sense. Relativity encodes the how far between things. What about reversibility? Sounds like we need to be able to work backwards.
You got it.
Yeah.
Reversibility just means every unique position has to get a unique ROPE code. If two different spots got the same code, you'd lose information. Right. The paper puts it simply, if Rx1 equals Rx2, then Rs1 must equal 2. It guarantees you don't accidentally merge positions during encoding. You could, in theory, get the original absolute position back.
Okay, got it. Understand relative positions for attention and keep track of the original absolute spots. Makes sense. Now, the paper jumps into Lie groups and Lie algebras. That sounds pretty heavy mathematically. Why is that needed for something like positional encoding?
Okay, yeah, this is where it gets really cool, I think. The paper uses this powerful math of symmetry and transformation that's Lie theory to give us a much deeper insight into ROPE.
Okay.
Think of Lie groups, specifically the special orthogonal group SON, as the set of all possible rotations in n-dimensional space. They preserve lengths and angles.
Rotation, like spinning things around.
Exactly, and that links intuitively to encoding position through rotation, which is ROPE's core idea.
So ROPE is fundamentally about rotations.
That's a key piece, yeah. And the Lie algebra, SON, associated with SON, that's the set of skew-symmetric matrices. Think of them as representing tiny infinitesimal rotations, the building blocks.
Like the starting point for a rotation.
Kind of. And the bridge between the algebra, those building blocks, and the group, the full rotations, is the matrix exponential. You take a skew-symmetric matrix X from SON, calculate XPX, and boom, you get a rotation matrix in SON.
Okay, so skew-symmetric matrices are the generators, and the matrix exponential turns them into the ROPE rotations we use.
You nailed it. And there's one super important property of that exponential. XTX plus Y equals XPX times XPY, only if X and Y commute, meaning XY has to equal YX.
Commute. Like, the order doesn't matter when you multiply them.
Right, and that becomes absolutely critical when we start thinking about multiple dimensions.
Because if a position has, say, 2 coordinates, you'd probably want to combine their encoding somehow.
Mm-hmm.
And this tells us the underlying generator matrices for those coordinates must commute for that combination to work nicely.
Exactly. The paper argues that Ropey's relativity property strongly points towards this exponential setup using skew-symmetric generator.
Okay, solid foundation laid. So let's revisit 1D Rho P, the original text version. How does this framework explain how that works?
Right, so remember the 1D relativity rule. R transpose M1 times RM2 equals RM2 minus M1. The paper shows if you assume R is a matrix exponential, like Rm equals XPMB, then for that rule to hold, B has to be skew-symmetric. B transpose equals minus B.
Okay.
And conveniently, any skew-symmetric matrix always commutes with its own transpose, so the other part of relativity is automatically satisfied.
Nice. And for the standard 1D Rho P, what's the specific B that gives us those sines and cosines we always see?
In the simplest 2D embedding space, N2, the B is just theta times the basic 0, 1, 1, 1, 0 matrix. Theta is the frequency.
Right.
You calculate the exponential of M times the B, so XPMB, and you get exactly the familiar 1D Rho P rotation. Cos bends, infin, sem bends.
Wow. Okay. So the math clicks perfectly with what's actually used. It just pops out naturally from this Lie algebra view. What about reversibility for 1D?
The paper points out that this mapping from position M to the rotation matrix arm is injective, meaning 1-to-1, within each rotation period, which is 2 divided by theta.
So as long as your positions don't wrap around too far.
Exactly. As long as positions stay within a reasonable range, which we usually control by picking the thetas, each position gets its own unique code. So yeah, 1D Rho P ticks both the relativity and reversibility boxes nicely.
That's really elegant. Okay, now let's level up to 2D Rho P. This is where the interaction or lack thereof becomes the main issue, right? How does the paper tackle this?
So for 2D, you've got coordinates like x1i, x2i. The relativity condition looks similar, but for 2 dimensions. R transpose of position 1 times R of position 2 equals R of position 2 minus position 1.
Okay, same idea, just in 2D.
And again, the paper suggests an exponential form, rx1i, x2i, x pi, x1i, b1 plus x2i, b2. Now, to satisfy relativity, we need 2 skew-symmetric matrices, b1 and b2. And the crucial part, they have to commute. b1, b2 must equal b to b1.
Ah, there's that commutativity requirement again, because we're combining 2 dimensions by 1 and by 2 with their generators, b1 and b2.
Precisely. So designing a valid 2D Rho P boils down to finding 2 skew-symmetric matrices in our embedding space, say so, ND, that commute.
How do we find those?
Well, the paper brings in another math tool. Any skew-symmetric matrix can be block diagonalized using an orthogonal matrix Q. You can transform B1 and B2 into a simpler form with 2 by 2 skew-symmetric blocks or zeros. Ideally, you find one Q that block diagonalizes both B1 and B2 at the same time.
Okay. And the standard 2D Rho P we often see, the one that just rotates each dimension independently. How does that fit in?
That standard version is actually the simplest case, where the orthogonal matrix Q is just the identity matrix. It means B1 and B2 are already block diagonal and act on completely separate parts of the embedding space.
Ah, so like if you're in 4D, B1 might rotate dimensions 1 and 2, and B2 rotates dimensions 3 and 4, with 0 crosstalk between them at the generator level.
Exactly. B1 affects the first pair, B2 affects the second pair, independently.
That explains the block diagonal structure of the standard 2D Rho P matrix we saw. It's literally 2 separate 1D Rho Ps side by side. And the paper said this independence is good for computation.
Absolutely. Because the dimensions are totally separate, you can compute the rotation for each 2D block super efficiently using Euler's formula with complex numbers. No need for expensive matrix exponentiation or trig functions every time.
But, and this is the big but, the paper also flags the major downside. It can't capture interactions between the dimensions. Why is that so bad?
Right. Since the rotations happen in isolated subspaces, the encoding for dimension 1 tells you nothing about dimension 2 and vice versa. So if there's a pattern that depends on the combination of coordinates, like that diagonal line example standard 2D Rho P, you just won't see it naturally.
Yeah, it knows the row, it knows the column, but it doesn't know they're changing together in a specific way, like moving diagonally. It misses the relationship.
Perfect analogy. It knows the coordinates, but not the story connecting them.
Okay, so the paper then mentions someone else, Hio et al., tried to fix this using mixed frequencies and learnable parameters on the sum of coordinates.
Yeah, that was an attempt. Instead of handling x1 and x2 separately, their idea involves rotations based on things like x1 plus bis2.
How does rotating based on the sum help catch interactions?
Well, by using the sum, the rotation does depend on both dimensions. If either x1 or x2 changes, the rotation changes. So it introduces a dependency, which might help capture those diagonal-ish relationships.
Okay, sounds promising.
Hmm.
But the paper raised a flag, didn't it? Something about losing linear independence between B1 and B2. What's the issue there?
The concern is that by making B1 and B2 effectively operate on this combined coordinate, they might no longer be truly independent generators for the original 2D space. This could mess with the reversibility. Ah, you might end up where different by 1 by 2 pairs get the same row P code, violating that unique encoding rule.
Exactly. You could potentially lose the ability to uniquely pinpoint the original position. It's a pretty significant potential trade-off.
So, gain some interaction, maybe lose some uniqueness.
Right. Though the paper does mention you might mitigate this problem in practice
Yeah.
by just using a bigger embedding dimension or more attention heads.
Yeah.
Give the model more room to figure things out.
Okay, so we've seen the Lie algebra view clarifies 1D and standard 2D row P and highlights this efficiency versus interaction trade-off in 2D. Now, the paper really generalizes this to n dimensions using maximal abelian subalgebras, or MESAs. Sounds very mathy. What are they?
It does sound jargony, yeah, but the ideas is actually pretty neat. Remember how for multiple dimensions, the generator matrices B1, B2, up to Bn all need to commute?
Yep, that was key for relativity. So a maximal abelian subalgebra, within our Lie algebra is basically a subspace where all the matrices inside it commute with each other. And it's maximal because you can't add anything else to it that still commutes with everything already in there.
So it's like the biggest possible collection of these skew symmetric matrices that all play nicely together, they all commute.
That's a great way to put it. They all mesh smoothly. And the size or dimension of a massa in SO is the floor of D divided by 2.
Okay.
Now, the paper's first big theoretical result, Theorem 1, basically says, n-dimensional row P can be built from a basis of the massa of SO 2n. If you pick n linearly independent commuting generators, B1 to Bn, from a massa of SO 2n, the rope you build using the matrix exponential will automatically satisfy both relativity and reversibility.
Whoa. Okay, so the massa gives us the blueprint for constructing valid ND row P. That's powerful.
It really is. It connects the abstract math to the practical construction.
And then the paper links this back to the standard ND row P, the simple extension of independent rotations. How does that fit the massa picture?
That's Theorem 2. It shows that standard ND row P corresponds exactly to a specific type of massa called the maximal toral subalgebra in SO2. This toral subalgebra naturally has that block diagonal structure.
Ah, so the B1, B2, etc. generators for standard row P form a basis for this specific simple massa.
Exactly. And when you exponentiate that basis, you get the standard ND row P matrix. Block diagonal with n independent 2x2 rotation blocks, one for each dimension.
So the standard way is just one specific easy choice from a massa. Guarantees the properties, but like the 2D case, no built-in interactions between dimensions.
Precisely. And Theorem 3 broadens this even more. It says even if your embedding dimension D is bigger than 2n, you can still make an n-dimensional row P by picking n independent generators from a massa of SO-D. They show an example using SO6 to make a 2D row P.
So there's flexibility. It's not just the standard way or nothing.
Right. There are choices. Standard row P from the toral subalgebra is efficient, well understood, but maybe limited. Using potentially more complex massas might let us model interactions.
But maybe at a higher computational cost.
That seems to be the core trade-off highlighted here. Simplicity and speed versus potential expressiveness for interdimensional stuff.
Which leads perfectly to the next big question.
Yeah.
How do we actually get those interactions between dimensions while keeping the nice row E properties like relativity and reversibility? The paper suggests learning a basis.
Right, but just learning arbitrary skew-symmetric matrices directly is tricky. You might not end up with ones that commute or that are linearly independent things you need for valid row E.
Okay, so direct learning is risky. What's the proposed alternative?
Their idea is more structured. First, you start with a basis of commuting independent skew-symmetric matrices, like from a massa, which we know works. Then you use a learnable orthogonal matrix, let's call it Q, to transform this initial safe basis.
So start with a known good basis, then use this Q matrix to kind of twist it or mix up the dimensions to introduce interactions.
Exactly. You're learning how to mix the dimensions via Q. The paper writes it like B equals Q times diag G1 times Q transpose. The J's are the original simple blocks, and Q does the mixing. The final ropey looks like Q times exponentiated blocks times Q transpose.
And Q has to be orthogonal. Why that specific type of matrix?
Using an orthogonal Q is key because it preserves important structures. It keeps things nicely behaved mathematically, and importantly, it helps maintain computational efficiency. That inner part, the exponentiated blocks, can often still be computed fast, maybe using complex numbers like before. The Q multiplication adds cost, but may be manageable.
Okay, so the problem becomes, how do we parameterize and learn this orthogonal matrix Q effectively? The paper looks at three ways. First up, the Cayley transform.
Yeah, the Cayley transform is one way to get an orthogonal matrix Q from a skew-symmetric matrix A. The formula is QIA times the inverse of I plus A.
Pros and cons.
Pro, it can be efficient to parameterize. You only need to define A cons. It doesn't cover all possible orthogonal matrices, so some interactions might be unreachable. And it can blow up numerically if I plus A isn't invertible. Plus, the interactions it learns are kind of global, not easy to interpret for specific dimension pairs.
Okay. Limited reach and potential instability.
Yeah.
Method 2, matrix exponential again.
Right. Here you just say Q is the exponential of some learnable skew-symmetric matrix A. Q is XPA.
Advantage.
Advantage.
Oh.
It can represent any orthogonal matrix smoothly, covers everything. Disadvantage. Calculating that matrix exponential can be really computationally expensive, especially for large dimensions. And like Cayley, the learned interactions aren't very localized or easy to interpret.
Got it. More expressive, but potentially way slower. All right. Option 3, Givens rotations. Sounds different.
It is. A Givens rotation is a simple rotation that only affects two specific dimensions, say dimension I and dimension J,
Yep.
and leaves all others untouched. It's a sparse matrix. The cool thing is, any orthogonal matrix can be built up by multiplying a sequence of these simple Givens rotations together.
Ah, so you build the complex Q out of simple targeted rotations.
Exactly. The big advantages are it automatically preserves orthogonality, and you get very interpretable localized control. You can explicitly learn the interaction strength between, say, dimension 1 and dimension 3.
That sounds really appealing, especially if you have ideas about which dimensions should interact. But the paper said the order matters.
Yeah, that's the catch. Because matrix multiplication isn't commutative, the final Q depends on the sequence you apply the Givens rotations in. AB is not BA generally, so you'd need to define a fixed order to make it consistent.
Interesting. So Cayley, fast, limited, exponential, complete, slow, Givens, interpretable, order dependent, each with its trade-offs. And they mentioned other possibilities too. Householder, Riemannian optimization.
Yeah, just briefly, those are other techniques for dealing with orthogonal matrices that might offer different pros and cons. Riemannian optimization is especially interesting for optimization on curved surfaces like the space of orthogonal matrices. Future work, perhaps.
We've definitely gone deep here.
Yeah.
From ropey basics through Lie theory, masses, to learning interactions via Q. Let's try to boil down the key takeaways.
Okay, yeah. So, big picture. This paper gives ropey a really solid mathematical footing using Lie theory. It shows relativity and reversibility are the non-negotiables, and it links building valid ND-ropey to finding bases in these maximal abelian subalgebras, these masses.
Right, and standard ropey, the efficient one everyone uses, that's just one specific mass of choice, the toral one. Simple, fast, but doesn't mix dimensions.
Exactly. And to get those interactions, the paper proposes starting with a valid mass basis and then learning an orthogonal matrix Q to mix things up. This could lead to more flexible, maybe more powerful positional encodings.
And we looked at the different ways to learn that Q Cayley, exponential, Givens, each with its own set of trade-offs between efficiency, expressiveness, and interpretability.
But it's really important to stress. This is mainly theoretical work right now. The paper lays the mathematical groundwork, but doesn't have, tons of experiments showing, look, this new interacting rope crushes standard ropey on task X.
Right, the practical proof is still needed.
Yeah. We still need to figure out when these learned interactions really help, and if the performance gain justifies any extra computational cost. That's the next step.
So compelling math, promising direction, but the real-world verdict depends on future experiments across different tasks and models. Will the extra smarts pay off?
We'll have to see.
Right.
Which kind of leads to a final thought for our listeners. Think about this. If we can move beyond just encoding simple sequences or grids independently and start truly capturing these subtle connections between different data dimensions, what could that unlock? Could it lead to totally new AI architectures, new capabilities? Think about data where the relationship between features is maybe even more important than the features themselves. Where could that deeper understanding of position and relation take us? Something to chew on.